All right, everyone. I want to do a video on SN2 versus SN1. This is a question that comes up a lot from students, which is how can I determine if I'm just given the reagents and I'm not shown the mechanism, if I have an SN2 or an SN1 set of conditions. And this is something that you can usually gather just from the synthetic steps or reagents that are present in the reaction being proposed. Certainly if you have access to the mechanism at an undergraduate level, you should know because SN2 is going to occur all in one step, whereas SN1 will have the carbocation and have multiple steps. But what happens if you're not given the mechanism and you only have the reagents in front of you, right? So your instructor gives you an exam and says, would this reaction most likely undergo SN2 or SN1, or they ask you to predict the mechanism and you're going to have to make that judgment call. How do you go about determining that? Because many students will say, well, we know SN1 from SN2 because SN1 has a carbocation. That's correct. However, when you're just looking at the reaction, you don't know whether the reaction is going to have a carbocation or not until you've determined that it's SN1. That's what will let you know that there's a carbocation. So how do we do this? Well, there's multiple things that we can discuss or talk about. All right, so the first one, and usually the most obvious one, is the position of the leaving group. And when we talk about this, okay, when I abbreviate LG, we're talking about leaving group. When we talk about position of the leaving group, we're talking about, is it in a primary position? Is it in a secondary position? Is it in a tertiary position? And this will usually help you. Now, you can have resonance stabilized positions like allylic and benzylic. That would be a separate discussion. But just using this, and we can include methyl here as well, right? This would be based off of the idea of if a carbocation is going to be left behind, where would it benefit from hyperconjugation and where would it get almost no hyperconjugation and therefore not form? So it turns out that if we're in tertiary, we will most definitely favor SN1. In fact, SN2 is not possible with tertiary leaving groups. So if I have something like a T-butyl chloride, or any sort of alkyl halide or tosylate, this group here is going to be subjected to an SN1. Now, we're not going to talk about elimination reactions in this particular lecture. I'm really just discussing SN2 versus SN1. So you do have to consider competing elimination reactions. But in a condition like this, if you ever saw tertiary, SN2 is not a possibility because there's too much steric hindrance. There are too many sterics or too much sterics around the leaving group. And because an SN2 requires the nucleophile to come in at the same time the leaving group is attempting to leave, right? So let's pick out a nucleophile here like H2O. Okay. If water was trying to come in as the chlorine is leaving, it's too crowded in this area. So the chlorine needs to leave, create a carbocation, and then the water could come in at that point. All right. So tertiary is only reserved for SN1. We are not going to have any SN2 associated with that. Secondary is difficult. So if you're handed a secondary substrate, you really are going to have to determine whether or not you have other conditions present that are going to favor SN1 or SN2. And we'll talk about those in this lecture. So that's sort of the one that's up in the air. It's very difficult to determine. I will just let you note, the closer you are to a more hindered secondary position, so let me draw one here, right? Let's say that this right here, here's our alkyl halide, and then you've got a very hindered area right here. You likely are not going to undergo an SN2 in this situation because, again, this is a fairly sterically hindered area. And even though this position right here is secondary, it's a secondary position next to a very hindered complex that's over to the left here. Not to mention that when a carbocation does form here, it could undergo a methyl shift. So you would be able to get a tertiary carbocation out of this. So sometimes if you have very hindered secondary positions, you can know that they're going to undergo an SN1. But if they're not that hindered, then it could be a debate for SN1 versus SN2. So that one's sort of left up in the air. Primaries are going to be SN2. You would not have primary carbocations, and even less, you would not have methyl carbocations. They would not exist whatsoever. SN2 would be for methyl and primary. So if I have a non-sterically hindered leaving group, right, something like this, a tosylate in a primary position, this is a very good candidate for SN2. There's not a lot of steric hindrance that's present there, and so the first rule is look at the position of the leaving group. If it's tertiary, you have a clear-cut SN1. If it's methyl or primary, you have a clear-cut SN2 when we're debating the type of substitution reaction that could occur. The secondary is really the one that's up in the air. So let's talk about other things that could potentially give away or let us know whether we have an SN1 or an SN2 going on. So don't save, open up a new one. All right, so first was position of leaving group. The second thing that you really want to consider is the type of nucleophile. Nucleophile. Okay, now when we talk about the type of nucleophile, I will just state that this usually will lead to either an SN1 or an SN2 if you can analyze it. However, it's not 100% all the time. So in other words, you could have certain SN1s that are occurring with an SN2 type nucleophile. You have to assess all things that are present. Okay, so when you're taking a look at this condition, for an SN2, we want a strong negatively charged nucleophile. So a strong negative charge, aggressive nucleophile. And when we do SN1, SN1 tends to favor a weaker neutral nucleophile. And we'll explain why here in a second. Okay, so if you think about an SN2, let's go back to that tosylate example. If I have a leaving group here, and this leaving group needs to leave, in an SN2 condition, I am required to bring in a nucleophile of some sort at the same time. So this nucleophile, because it's a bimolecular reaction, this nucleophile has to get in there as the leaving group is leaving. We can't have the leaving group leave a carbocation behind and then wait for the nucleophile to come. That would be an SN1 type condition. So in this case, because the nucleophile needs to cooperate at the same time the leaving group is leaving, we are looking for a strong nucleophile. Strong nucleophiles tend to promote SN2, all right, and negatively charged nucleophiles tend to be a good sign of their strength. So when you have a negatively charged nucleophile, it's got extra electrons. It's really looking to act as a base or nucleophile to donate those electrons, right? A Lewis base. And so the fact that we're using a strong nucleophile, a negatively charged nucleophile, allows this nucleophile to sort of aggressively go after the partial positive charge that's here as the leaving group is leaving. We need a nucleophile with enough oomph or enough driving power to get in there and perform that backside attack. Okay, in an SN1, we sort of have the opposite situation. So let's go back to our terbutyl example. In a situation like this, we're not looking for a super high energy nucleophile, and in fact the kinetics of SN1 are unimolecular, and so the only thing that matters is getting our leaving group out of the way. We don't want a nucleophile trying to come in to a sterically hindered area as a large leaving group is trying to get out of the way. And so neutral nucleophiles that aren't going to be quite as aggressive and be interfering with that process tend to be favored here. And so you will find a lot of times something like water, okay, or methanol. These are great nucleophiles, right? You could have things like sulfur nucleophiles that are neutral. You could have phosphorus nucleophiles that are neutral. All of these would be fantastic options for SN1 because they don't have the same level of aggressiveness in terms of their nucleophilicity or their nucleophilic behavior. They kind of chill out in solution and wait until that carbocation is formed, and then they go in and perform that attack. And remember, in SN1, the rate limiting step is the formation of the carbocation. So your neutral nucleophile, you don't need something aggressive. That's going to happen instantaneously as soon as the carbocation forms. All right, so that's sort of a reasoning behind that. So if I saw a hydroxide, I would probably be inclined to think SN2. And keep in mind, a lot of students forget, if I write sodium hydroxide, right, while this may not directly have a charge written with it, this is an ionic compound. So in solution, this becomes Na plus and OH minus. So keep in mind, if you're dealing with salts, you're really being handed a negatively charged nucleophile. So don't get confused with that. All right, and then the next thing after the nucleophile is going to be the solvent. So when we start talking about solvents, the SN2, okay, so this is number 3 on our list. The SN2 is going to favor polar aprotic solvents, and the SN1 is going to favor polar protic solvents. All right, so why is this the case? Well, it turns out if you look at your nucleophile in an SN2, well, before that, all right, so let's back up. What does it mean to be polar protic? In case people are wondering, it means that you have NH bonds or OH bonds. And technically, an FH bond would count as well, but that's a substance within itself. That's hydrofluoric acid. And almost no chemical reaction is going to utilize hydrofluoric acid as your solvent. There's just better options for solvents. Hydrofluoric acid is very corrosive. It's very damaging to biological systems, so you're probably not going to use that very often. All right, but it would have hydrogen bonding, making it polar protic. But any type of alcohol, water, any sort of amine like triethylamine, well, triethylamine doesn't have the H there, but any of those amine solvents or alcohols, waters, those would all be polar protic. So methanol, ethanol, water, etc. Okay, and then when you have polar aprotic, it means you still need a polar solvent. So there should be some level of dipoles with the solvent. We wouldn't want something like hexane or a non-polar compound. But for instance, acetone would be a good example here. Acetonitrile would be a good example because you have that CN bond that's highly polar. There's something known as DMF, DMSO. Those are all polar, highly polar solvents, but they are aprotic, meaning they don't contain any OH or NH bonds. And what we're dealing with here is really hydrogen bonding. Does my solvent have the capacity to undergo hydrogen bonding? So in an SN2, think about the types of nucleophiles. We're dealing with these strong negatively charged nucleophiles, right? So maybe something like a hydroxide. Now keep in mind, the solvent, okay, hydroxide as a nucleophile is different than having some sort of alcohol group as a solvent, because you're going to have much more solvent around than you're going to have nucleophile, and that solvent is going to attempt to hydrogen bond with the nucleophile. So if I had something like this, right, this is favoring an SN2 type of condition. If I had something like water, water has these highly polarized bonds capable of hydrogen bonding, so they are going to help stabilize, right? They're going to surround themselves and attempt to stabilize these hydroxide ions. So what happens when they do that? Well, the more water molecules that come by and start to basically surround themselves around this nucleophile, the more stable the nucleophile becomes. So when this occurs, you're taking the nucleophile and you're going to lower its energy. And that's a problem, because in an SN2 situation, you need an aggressive nucleophile, a nucleophile that goes in and attacks at the same time the leaving group is leaving. So what we're doing is we're taking a highly aggressive nucleophile that's ready to go, and we're sort of squashing its energy. We're saying, nope, you can just hang out in solution. All of the hydrogen bonding here will help stabilize you. And that is not an ideal situation for an SN2. So we do need polar solvents because we need nucleophiles, especially negatively charged nucleophiles, and alkyl halides tend to have some polarity to them. So like dissolves like, we do need polar, but we want aprotic solvents, right? So we do not want the ability for hydrogen bonding in SN2 because what's going to happen is the nucleophile's energy is going to get squashed. That's going to greatly increase the energy of activation for the reaction because now we have the reactant energy is being lowered to a large degree, right? Reactants, the nucleophile is a reactant. And so that makes it more difficult for this reaction to occur. The leaving group's getting ready to leave. The nucleophile is nowhere to be found because it's being stabilized by the hydrogen bonding process. That's bad. In an SN1, the complete opposite is going to happen. All right. So in an SN1, we don't need the nucleophile to get in and to bond with the substrate as the leaving group is leaving. In fact, we want it far away. We want the leaving group to leave on its own and give it plenty of room. And then once a carbocation forms, we can start looking at the nucleophile coming in. So think about it. If I have a leaving group in a tertiary position, the leaving group leaves, I now have a carbocation. And the hydrogen bonding is going to do the same thing here that it did with the nucleophile in an SN2 situation. So now I'm going to have some hydrogen bonding in the proximity of the carbocation, and this is going to help lower the energy of the carbocation and stabilize its formation. So what happens with polar protic solvents? Their hydrogen bonding is going to be beneficial in terms of promoting carbocation formation because the carbocation knows once it forms that there's in its proximity there's hydrogen bonding that can occur to help sort of lower its energy, make it a little bit more stable. So in this case, polar protic is going to promote this forming. The polar protic solvents will help promote carbocations forming. Okay, so that's a look at the conditions that can help favor SN1 and SN2 conditions. So let me bring up the screen here. All right, so to recap, all right, number one, you want to take a look at the position of the leaving group. Tertiary is going to favor SN1, whereas methyl and primary will favor SN2. Secondary, look at the solvent and look at the nucleophile. You need to make other determinations in that case. For your nucleophile, if you find salts, strong negatively charged nucleophiles, you're most likely headed towards an SN2. If you find neutral nucleophiles, especially things like water or methanol, which can act as both a solvent and a nucleophile, then you are most likely headed towards SN1 type conditions. And then number three, you need to consider your solvent. That's a very big driving factor in this. If you have polar aprotic solvents, you're going to favor your SN2. If you have polar protic solvents, you're going to favor your SN1. So remember, hydrogen bonding, anything that could do hydrogen bonding, is going to favor SN1 type conditions because it will stabilize the formation of the carbocation. Okay? So those are the three major driving factors in determining that. Now I will mention, if you are given the reactants, what goes over the arrow, so the reagents, and then you have the product present, there is a fourth technique you can use, which is to analyze the products. If you have a mixture of your products, a racemic mixture, or you have attack from both sides, meaning the nucleophile added from the front and from the back, you add an SN1 because only carbocations are going to allow for that type of behavior in a substitution reaction. If you have 100% inversion, so let's say that your leaving group is wedged out of the plane on that thick wedged bond. You have a bromine that leaves there and all of a sudden a hydroxyl comes in and you find that the only product is with the hydroxyl dashed in the back. That's 100% inversion, and that is a sign of SN2 because SN2 does not have that trigonal planar intermediate that can be attacked from both sides. It can only be attacked through a backside attack, which will invert the stereochemistry. So I hope you guys found this video useful. Please remember to like and thumbs up if you enjoyed it. I am happy to take any questions, so leave them in the comments below. I will also try to leave a link to my substitution playlist, which goes into basically all of these conditions and SN1 versus SN2 in more detail. So I will see you guys next time, and please remember to subscribe for all the latest content that comes out. Take care.